Okay, today's lecture is going to be about torque. No, Nicki Minaj has nothing to do with this. So, I'm not going to get through. We're going to make this kind of short and sweet. We've discovered that there is a rotational analog for displacement, that there is a rotational analog for velocity, okay, which is delta theta and omega, and there's one for alpha, which is, and one for, acceleration, which is alpha. We have one for energy. Okay, energy equals 1/2 mv squared. Okay, and it also equals 1/2, well then I omega squared, which means we needed one for mass, which is I, and so we have all these, we're developing these rotational analogs for our linear measurements. Well, we have a new one because in order to make things turn, okay, and to change their state of rotation, we have to exert a force that compensates for the radius from the center of rotation, and that is called torque, and we give it a value tau. Okay, the letter is tau. Okay, this is not related to the tau cannon that you see in Half-Life 2 that's mounted on the buggy when you go on. Okay, tau, just as force, we now have one for force. It is called torque, and just as force equals mass times acceleration, our tau is going to equal our rotational mass, which is our I, our moment of inertia, times our acceleration, our rotational acceleration, which is alpha. And so anything that causes, this is our equivalent of F equals ma for rotational motion. Okay, and Newton's laws still apply. Okay, you can, Newton's first law of inertia, if because this winds up being a net torque. Okay, gives you your net. The sum of your torques is your I alpha. It's the same thing. The sum of your forces equals your net force. It's the same idea. So let's have a. Here is our rotating body here that has an axis there and here. And this body has two pegs on it. It's got one out here. This is a vertical, it's coming out of the page. Okay, we've got a peg stuck in this hole right here, and we've got another peg stuck right here. Okay, we have two people pulling. Okay, so we're gonna have a force. Okay, we're gonna have a force in that direction, pulling on this peg, and this peg is at a, that's at R1 here, and this is going to be force 1 for our spot, our place 1. And then we're going to have another radius here for, okay, this is R2 for a force that's going in the other direction. All right. What we are creating here is two different torques that are acting on our object. All right. We can add them together. Okay. This is going to create a torque 1 and a torque 2, and our net torque is going to equal the sum, T1 plus T2 plus however many torques we have on this object. You with me there? Okay. So what winds up happening is if we have an imbalance in our torques, if we have one pulling this way, let's say force 2 and force 1 are equivalent forces. Okay. because, well, and you guys have messed with this before, if you pull on something, if you have a longer lever, okay, you don't have to exert as much force on it to turn it. Okay, it's one of the origins of the term leverage. Okay, the longer lever, the more torque you're able to exert on an object, and that's, that's how it works. Well, this is some of our torques, but we find out that our torque also equals, this I alpha also equals the R times the force that's exerted at the distance. So our torque 1 is going to be our R1 times our force 1, and we're going to have our torque 2, this should be a curvy thing here, torque 2 is going to equal R2 times F2. Now these are just the magnitudes so far. And this is also only if the force is perpendicular. Only if the force is perpendicular. Okay, which is going to bring us to our example here. We have a bracket on the ground here. It's got a pin, and it's fixing an arm. I don't want to draw it at an angle. Hold on. Okay, I want you to assume that this is another rod of length L. Okay, rod of length L, negligible mass. And fixed at one end. Yeah? So, we are going to exert a torque on this, okay, but we're going to pull on this with a force that's in that direction. Okay, it has a distance R. Okay, so, because these two are not orthogonal, we need to break the force up into its components. We're going to have a force in that direction, and we're going to have a force in that direction. Only the force that is perpendicular to the radius actually applies into the torque. Okay, so how do we determine this? Well, what is this? If this is the angle right here, that this is our theta, the angle that the force is applying to our rod, what is this force over here going to be? This is going to be force sine theta right there. So our torque winds up being our radius. Okay, or actually I don't want to vector that yet. Our radius times our force times the sine of the angle in between them. Yeah? This is going to equal our torque here. Now, we mentioned the other day, we kind of blew past it, but torque, or this product, this R times F, because this is also a vector, okay, we have to have a way of multiplying these and still winding up with a direction, because we can pull a force in one direction, the force can go in the other direction, and we're still multiplying them, but we need to indicate that there's still a direction to what's going on here. And this becomes, our torque equals R cross F. And this is our first vector cross product, and we're going to have a lecture on that. I'll probably give you a lecture on that to watch over break for our vector product. And we talked a little bit about this before, that if you In fact, I need to start a new program here. That with our, so this right here then becomes, okay, so that's our vector tau. This right here is the magnitude of our torque. Okay, RF sine theta is the magnitude, but the direction of it is going to be all right. So here's, let me put these where you guys can see them. Here's our radius. There's our force. Okay, we put our hands in the direction of the radius, and then curl it into the direction of the force. Yeah? Wherever the force is, even if it's only at that angle, we curl our fingers that way, and whichever way our fingers work to curl, okay, that's the direction of our force. Right up there. Okay. All right, so that's, yeah, so and that's the right hand rule, and that's, so we create we create a magnitude for our vector using AB, first vector, second vector, sine theta, and we have a direction to that vector, which is given by the right hand rule, and up. Now, we can use this, and let me just get that out of here. What are you going to use that for? Oh, right, and so this is also how, by the way, our x, y, and z axes are made. That x curled into y points in the z direction. Y cross z points in that direction, and z cross x points in the y direction. Follow me there? So use your hands and you do the whole right hand rule, whatever it is. Okay, or in vector notation, it's I cross j equals k. Okay, j cross k equals I, and k cross I equals j. And these are order specific. We talked last time that they are not commutative. They have to be in this particular order. Otherwise, you get the negative value. Okay. I do want to get through an example problem with you guys. So let's find one of those, and then we'll be right back. Okay, so we're going to do exercise, we're going to do example number 1012 on page 310. Okay, and this is the angular acceleration of a wheel. So what we have here is a wheel. Okay, so we're given a wheel of radius r. Okay, mass m, moment of inertia I, oh look, it's just there given to us, okay, is mounted on a frictionless horizontal axle. So we're going to rotational ones, by the way, truly test your drawing skills. So, yes, we come to the land of ice and snow. You don't know the rest of that song. Okay. Okay, so we have a wheel of radius r, mass m, and rotational inertia I is mounted on a frictionless horizontal axle. Okay, is allowed to spin. In fact, I need to draw another little thing in here. All right, so it's Yeah, it's not great, but we'll take it. There we go. Okay, a light cord wrapped around the reel supports an object of mass m. So we have suspended from this is a object of mass m. This is mass m. All right. We need to calculate the angular acceleration of the wheel, the linear acceleration of the object, and the tension in the cord. So, solve. Okay, what's the first thing you do when we have a diagram and picture, that sort of stuff? We create a free body diagram. Excellent. Our free body diagrams now include torques. So, if we're just looking at this guy right here, just this mass, he has what? He's got tension, he's got mg. They are not necessarily equal, but we know that T minus mg equals ma, whatever that's going to be over here. Okay, so we'll just kind of put this aside for right now, because we know that's going to come back to bite us in the future. All right. Now, we also just have a torque on this, okay, on this wheel here. So, we know that the sum of our torques equals I alpha. Okay, but we also know that what is the torque acting on this thing? Well, what's the only force acting on this? Well, we've got, this has, in fact, let me change colors here to better illustrate. Okay, that we have this right here. Okay, this is our R, and this perpendicular down is also our tension. Yeah? So this is the torque acting on the wheel, is our tension down acting at this radius. So we know that this equals TR. Okay, you good so far? All right. That means that alpha is going to equal our tension times our radius divided by our moment. All right. Now, we also know now this is where this guy comes back to haunt us in the butt, or to bite us in the butt. If we're taking this tension down, if we're going to take this tension to be positive, then this tension up here needs to be negative. So we can flip this guy around and we can do mg minus t also equals ma. You guys with on that? Yeah. Okay, it doesn't really matter just as long as one's opposite the other, but it needs to be consistent with the other part of it. So if we're going to take, I'm going to take this tension acting on the wheel to be positive. That means down is positive for tension, up is positive for tension over here. Gravity has to be positive. All right. So our tension is then going to equal ma plus, I'm sorry, no. This I can figure out, but I can't do this. Why aren't you erasing? I can draw, but it's not letting me erase. All right, so our tension all right, due to circumstances out of my control, we needed to switch to our other version here. So, sorry for the abrupt visual change. All right, so here's our tension. We found out over here that our tension is going to equal mg minus mg equals our negative tension, which means tension equals mg minus ma, which, okay. which was part of the problem I was trying to fix to begin with. So, so now we can plug this into our tension here, and we're going to get our alpha equals m g minus a r over I. Okay, or we can yes, that would work, but we also have, but we need to find a. So hold on, we're gonna go another direction here. Sorry, guys. Okay, from here, we're gonna solve for a. Okay, so our tension is going to equal. I'm sorry, or a is going to equal mg minus t over m. Okay, and we also know that this a, because that's the acceleration of this guy. Okay. Okay, our acceleration is going to equal r alpha. Oh, that's off the screen. Because we know that acceleration equals r alpha, or there. All right, but what was alpha but tr squared I? So now we can actually solve for t. So mg minus t over m equals t r squared over I. Follow me there? tr times r, tr times r, all over I. Okay, and then from here we just solve for t, and this just gets a little messy, but it's not that big of a deal. Mg minus t equals mtr squared over I. Oh, that's just ugly. Alright, so we're going to add t to both sides. This sucks. mg equals t 1 minus mr squared, or 1 plus mr squared over I, and then we divide this by that, and it's mg over 1 plus mr squared over I. Oh, you can't see that. Okay, that is our tension. All right. So that's tension. So now okay, we can now use this to solve for, we come back over here and we start plugging in for what A is going to be. And if you need me to do that algebra, we can. So I really don't want to. So we're not.